Good morning everyone. The part 3 of the lesson chemical kinetics is order of a reaction. Now here we have to find the order of a reaction. So the dependence of the reaction rate on concentration may be expressed in terms of the order of a reaction. So to calculate the order of a reaction, we must carry out the experiments to find out the dependence of reaction rate on the concentration of each individual reactant at a given temperature. The concentration dependence of various reactant, as we have seen or as we have discussed earlier, is given by the rate law, and thus the order of reaction is defined as the sum of the power. The order of reaction is defined as the sum of the power to which the concentration terms are raised in the rate law equation to express the observed rate of the reaction. So the power of the concentration of a particular reactant in a rate law is called the order of the reaction with respect to that reactant. So let us consider a reaction, and if the rate of reaction is, that is, we have a reaction AA plus BB plus CC gives product. For example, we have this reaction. So if we want to find the rate for that reaction, rate law, so rate is equals to minus dx upon dt is equals to k, that is A, then B, and then C. Then the order of reaction. So for that, the order of reaction, it is represented by N. So for that, the order of reaction is equal to A plus B plus C. This is the sum of the power. It's called the order of reaction, where A, B, C are the order with respect to the individual reactant, that is A, B and C, and the overall order of reaction is the sum of these exponent, that is A plus B plus C. When N is equal to 1, now we have such type of a condition where we have N is equal to 1 or N is equal to 2. So when N is equals to 1, the reaction is said to be first order. When N is equal to 1 means the reaction is said to be first order. When N is equal to 2, the reaction is said to be second order reaction, and so on. Now let us take some examples, some common example of reaction for the different orders. So first of all, let us discuss the reaction for first order. Reaction for first order. And the best example of the reaction for first order is the decomposition of nitrogen pentoxide, that is N2O5. When the decomposition of nitrogen pentoxide takes place, we get nitrogen dioxide plus half O2. Now for that reaction, rate is equals to K, that is N2O5. So this one is the example of the reaction for the first order, and this is the rate is expressed for the first order of reaction. Now the next example is the decomposition of ammonium nitrate, that is ammonium nitrite, not nitrate, NH4 NO2. So when the decomposition of ammonium nitrite takes place, we get N2 plus 2H2O. Now if we want to express the rate of this reaction, so rate is equal to K NH4 NO2. So this one is also the example for the first order, example of reaction for the first order of for first order. So these are the first order in which the value of N is equals to the 1. Now the second one is the reaction of second order. Reaction of second order. Now it is clear that when the value of N is equals to 2 and so on. So when N is equal to 2, it is called the second order. Now let us take some example of second order of reaction. Now for that, the reaction is the decomposition of nitrogen peroxide, that is 2NO2. Now the decomposition of nitrogen peroxide takes place. We get nitric oxide plus oxygen. Now the rate is equals to NO2 square. So here the value of N is equals to 2. So this is the second order of reaction. Now the another example for the second reaction for the second order of reaction is, that is a reaction between H2 and I2. Reaction between hydrogen and iodide. So for that, H2 plus I2 gives 2HI. So this is the example of the reaction for the second order. Now if we want to find out the rate, so we have two reactant here. So rate is equals to, that is K H2, and this one second one is the I2. So 1 plus 1 is equal to 2. Here the value of K, that is rate is equals to 2. Order is equal to 2. That is 1 plus 1 is equal to 2. So this is the second order reaction. Now let us discuss the reaction for the third order. Now the reaction for the third order is the reaction between nitric oxide and oxygen, that is 2NO plus O2. It gives 2NO2. Now for that, if we want to find the rate, so rate is equal to, that is NO whole square, and that is O2. Now the order is 2 plus 1 is equal to 3, that is 2, and plus this one is this entity is as a 1. So 2 plus 1 is equal to 3. So the order of reaction is 3. Next example is the reaction between nitric oxide and the Cl. So that is 2NO plus Cl2. So we get 2NOCl. 2NOCl. For that, the rate is equals to K, that is NO whole square, and here we have Cl. So 2 plus 1 is equal to 3. So here the order is 3. So this is the example for the third order of reaction. The last one is the zero order reaction. This is the last topic in the order of reaction, that is a zero order reaction. So a number of zero order reactions are known. A numbers of zero order reactions are known in which the rate of the reaction is independent of the concentration of the reactant. Now for example, the best example is the decomposition of ammonia. The decomposition of ammonia at the surface of metal like gold, platinum, etc. is the best example for the zero order of reaction. Now we know that is the decomposition of ammonia is, this is the ammonia, 2NH3 is the ammonia, and it is converted into N2 plus 3H2. This is the Haber's process. Here the temperature is 1130 Kelvin, and in the presence of platinum as a here the platinum act as a catalyst. So it has been observed that the rate of the reaction is independent of the concentration of ammonia. In this reaction, the rate of the reaction is independent of the concentration of the ammonia. And how it is independent? Let us I'll show you this one. So for that reaction, the rate is equals to minus dx upon dt. That is, now k is equals, that is k is equal to k ns3, and here it is a 0. Or we can say that rate is equal to, if its value is 0, so rate is equals to k. Here the order of reaction is how much? 0. 0 is the order of a reaction. So in this reaction, platinum metal, here we are talking about we have already discussed about the platinum metal. So in this reaction, the platinum metal act as a catalyst. At sufficiently high pressure of ammonia, the metal surface get fully saturated with gas molecule, and on further increasing the concentration of ammonia, the amount of ammonia on the surface of the catalyst does not change. Therefore, the rate of reaction becomes independent of the concentration and hence becomes zero order. That's why it is a zero order reaction. Now the next topic is unit of reaction rate constant. So the unit of rate is, the rate is change in concentration with time. Therefore, the rate of a reaction is expressed by the concentration unit divided by time units. If the concentration are expressed in mole per liter and time in second, then the unit for the rate of reactions are, that is, mole per liter per second. This is the unit for the rate of the reaction. How? That is, rate is equal to change in concentration, that is the concentration with time, and we know that the unit of concentration is, that is, mole per liter, and the unit of the time is second. So the unit is, that is, mole per liter per second is the unit for the reaction rate. Now the unit of the reaction constant, if we want to find out the unit of the reaction constant, so the unit of reaction constant are different orders of different order are different. So for all the type order or type of the order, the unit is different, and this can be elaborated as, so first of all we have to find out the unit of rate constant, unit of rate constant for zero order reaction. So first of all we have to find out the unit of rate constant for the zero order reaction. So for zero order reaction, the rate may be expressed as, that is, rate is equal to K. A is the concentration, it is 0, concentration is 0, so rate is equal to K. So rate is mole per liter per second is equal to K. This is the unit. So the unit of K is equal to mole per liter per second. Now this is the unit of rate constant. This is the unit, K is the rate constant. So this is the unit of rate constant for the zero order of reaction. Now the second is the unit of rate constant for first order reaction. This is the unit of rate constant. Keep in mind, here we are finding the unit of rate constant for the first order of reaction. So it is, we have discussed this earlier, that for first order of reaction the rate may be expressed as rate is equal to Ka. This is the rate. So rate is mole per liter per second is equal to K. Again, the unit of the concentration is mole per liter is the unit of the concentration. So that now K is equal to per second. Now this is the unit of the rate constant for the first order of reaction. By this method we can easily calculate the unit of rate constant for the zero order, first order, second order and the third order. Now next point is for the second order reaction. Now this is the second order reaction. So we know very well for the second order of reaction, the rate may be expressed as rate is equal to Ka and its power is 2. So that is mole per liter per second is equal to K mole. This is per liter whole square. This is per liter and this is the whole square of per liter. So at last we get K is equal to 1 upon mole per liter second is equal to liter per mole per, that is, second. So this is the unit of the rate constant for the second order of reaction. Now the last one is for the third order reaction. This is for the third order reaction. We know that for third order reaction rate is equal to K a to the power 3. So for that we know very well that is mole per liter per second is equal to this K, that is mole per liter, that is whole 3 or whole cube. So at last we get K is equal to 1 upon mole square L minus 2 S is equal to L square, that is mole per square and second. So this is the unit of rate constant for the third order of reaction. Now by this method we can easily find out the unit of rate constant for the zero order reaction, first order reaction, second order reaction and the third order reaction. Now in case of the gaseous reaction, the concentration are expressed in terms of a pressure and the unit is atmosphere. Therefore the rate has the unit of atmosphere per second in place of the mole per liter. Atmosphere per second is the unit and thus the unit of the different rate constant would be. So first of all discuss the case of the zero order of reaction in case of the gaseous, if we are talking about the gaseous reaction. So for the gaseous reaction the unit of the rate constant for zero order of reaction is atmosphere per second. For first order of reaction is per second, that is same. For the second order of this is the for the second order of reaction. So for second order of reaction is per atmosphere per second, and for the third order of reaction is, that is, atmosphere per second. So these are the units in case of the gaseous reaction. The units are changed because for the gaseous reaction we have taken the concept of the pressure and we know that the unit of the pressure is atmosphere. Now the next topic is molecularity, that is molecularity of a reaction. Molecularity of a reaction. So according to the collision theory, a chemical reaction for a chemical reaction to occur, the reactant molecule must collide with each other. So when the reactant molecule collide with each other, they give the product. So the number of reacting species, now here I am using the word reacting species. So here the meaning of reacting species is maybe the molecule, maybe the atoms, or maybe the ion. So the number of the reacting species which collide simultaneously to bring about a chemical reaction. When the reactant molecule collide, then definitely there will be a chemical reaction when we get a product, and is called the molecularity of a reaction. So if a reaction involves the decomposition of only a single species, the molecularity is 1. Here the reaction involves the decomposition of only a single species, therefore its molecularity is 1, and it is called unimolecular reaction. Uni means 1, so it is called the unimolecular reaction. So for example, the decomposition of hydrogen peroxide, the decomposition of hydrogen peroxide involves single species which undergo the change to form the product. So the formula for the hydrogen peroxide is H2O2. Now here it is a single species which undergoes decomposition to give the product, and the product of its is, that is H2O plus half O2. Since here only single species undergoes decomposition, that's why it is known as the uni means 1, unimolecular reaction. This is a unimolecular reaction. And if we are talking about the decomposition of ammonium nitrate, the formula for the ammonium nitrate is NH4NO2. This is the ammonium nitrate. Now if it decomposes, we get N2 plus 2H2O. So the decomposition of ammonium nitrate, here again we have using the single species which undergoes decomposition. So this is also the example of unimolecular reaction, because it involves only one reacting species. This is also only one reacting species. This one is also only one reacting species. So similarly to that, if the reaction involves the collision of the two species, if two species are collide to give the product, it means it is a 2 means bi, so that time it is known as the bimolecular. And if the three species take part in the collision to lead the formation of the product, that time it is termed as a trimolecular, and so on. So let us discuss the example of a bimolecule. This is these two are the example of the unimolecular reaction. And if we are talking about the bimolecular reaction, so the best example for that is the dissociation of hydrogen iodide, that is 2Hi. Now when the hydrogen iodide dissociate, it gives H2 plus I2. Now here the two species take part in the collision. One is the hydrogen and second one is the iodide. That's why it is known as the bimolecular, that is the bimolecular reaction. This is the example of the bimolecular reaction. Now if we are talking about the trimolecular reaction, so it is the 2NO plus O2. It gives 2NO2. Now here in this reaction, this is the reaction of the nitric oxide and oxygen. It is a trimolecular reaction because it involves the collision of three reacting molecule, 1, 2, 3. It involves the collision of the three reacting molecule. That's why it is known as this is called the trimolecular. This is the trimolecular reaction. So this is the molecularity. Now today we have discussed the two topics. One is the molecularity and another one is the order of reaction. And if we want to distinguish between the order of reaction and the molecularity of the reaction, so there are some important concepts. The first is the order of reaction is determined experimentally. Order of reaction is determined experimentally, whereas the molecularity is a theoretical concept. Order of reaction, it is an experimental concept, and the molecularity is a theoretical concept. The order of reaction can be zero. We have already discussed the order of reaction for the that is zero order of reaction. So the order of reaction can be zero, but the molecularity of a reaction cannot be zero because it depends on the collision of the reacting species. So it is not possible that it would be zero. And the order of reaction means the sum of the power. Order of reaction is the sum of the power of concentration terms. And molecularity means molecularity is the number of the reacting species. The molecularity is the number of the reacting species undergoing continuous collision by the simple reaction. So these are the main and the important important difference. And one more important difference is order of a reaction need not to be a whole number. It can have a fractional values also, but if we are talking about the molecularity, so the molecularity has a whole number. It has a whole number values only, that is 1 2 3 etc., and it cannot be integer. It cannot be non-integer, sorry, it cannot be non-integer.